Welcome everyone, and thank you for joining us today. I'm going to give you a tour of one of Enthought's professional development training courses that we are calling the Machine Learning Mastery Workshop. My name is Dylan, and I'm one of the technical trainers here at Enthought, and today I'm going to be telling you about Enthought, who we are and what we do, for those of you who might not be familiar with our work. The bulk of the time in this webinar is going to be spent talking about a particular training offering, who it's for, what's in it, why you might want to attend, but this itself is not the training session. At the end, we'll have some time to answer any questions that you post during a Q&A session, and we also have a staff member here on site to answer questions that you might have during the live recording of the webinar, so please feel free to answer your questions into the question box as we go. And then finally, everyone who has registered for this webinar will receive a link to a recording in a couple of days. Enthought is a company that was founded in 2001 that provides scientific solutions for computing. Now, I think that most people have some idea what scientists do, and I also think that most people have a good intuition about what computers do, but in our experience, most people do not have a great idea about what happens when these two things are combined. So I would quickly like to go through one specific example of the kind of work that Enthought does. If you are a financial firm, one of the things that you're very concerned with is estimating the risk created by your current holdings. One of the reasons for this is that institutions like banks are required to keep a certain amount of liquid assets to meet their financial obligations during market downturns. To know how much money you need in your vaults, you need to know how much money you stand to lose on any particular day. And looking at things the other way around, trading firms need a way to dial up or down the risk in their portfolios so that they're leveraging as much of their capital as they can without any undue risk of bankruptcy. The most widely method used of risk estimation, the one that's used by most of the banking regulators, looks at the past variance of instrument values and uses them to compute a confidence interval for their values in the current market. This method has the benefit of being relatively straightforward, but the disadvantage of being unresponsive to recent financial events. So Enthought created a parametric method for calculating risk that is capable of incorporating information like seasonal patterns in value and nonlinear interactions between instruments. So that's what we mean when we say scientific computing. We don't sell software for the sake of software. The software is always in the service of some analytic process or analytic product. And Enthought has been a global leader in that kind of computing for 15 years. We work in C, C++, and Python, and in recent years have been doing a lot more work with artificial intelligence-enabled solutions for oil and gas, for manufacturing, for finance, for biotech, and others. In addition to our consulting work, we create software tools. Some of these are tools that we built internally for rapid prototyping of software applications and have since been released as free and open source software. Others are licensed solutions for common pain points, like provisioning Python environments inside of secure air-gapped networks. Still others are tailored to individual industries, like the geological sciences. So for example, you may have seen Enthought's virtual core software in the news recently related to the analysis of core samples from the Chicxulub crater. Enthought is also the provider of the gold standard of training solutions for the Python programming language, and that's what we're here to talk about today. We'll be focusing on one specific class that we're going to offer on an ongoing basis because it is so widely applicable. But as a company, we also provide training solutions that are tied to customers' business areas, like oil and gas, or specifically to their business models and software stacks. The final cornerstone of our business is enterprise support for Python. And the easiest comparison to make here is with Red Hat, who builds and distributes the open source Linux operating system for enterprise clients. Now we do something similar for Python in terms of testing and building those Python packages, but sometimes they rely on libraries that are written in C and Fortran, so we take care of that compilation step and then also purchase the necessary license that let us link against the newest versions of things like Intel's math kernel library. Globally, we have over 1 million downloads of our software products, and we are a global company. So we are headquartered in the great state of Texas, and we maintain offices in Cambridge in the UK, as well as Mumbai and Chennai in India. These software products include a Python distribution, for which we build and test the most useful scientific Python packages, a lightweight Python IDE to support the creation of Python programs, and a deployment server that allows you to manage the packaging and distribution of those proprietary Python programs. The products that you see listed on this slide are all things that we use internally at Enthought because they allow us to work more productively, and we think they'll do the same for you. We are also global in the non-literal sense in that we have reach into many different business sectors. Now, this includes sectors that historically have had a strong interest in machine learning algorithms like finance and marketing, and others which have begun to explore that space more recently, like the biosciences and energy. Our consultants have doctorates in relevant STEM fields, and the expertise in the company is very, very diverse, so we can enter into any industry and rapidly become productive. Now, today, I would like to mainly talk about our training offerings. So we have open classes for individuals, where you can register for a class nearby and attend with other individuals who have registered the same way. We also offer corporate on-site classes where we send a trainer to your location to train a team which needs to be onboarded to Python or to machine learning or to NumPy. Larger companies will often need to train dozens or scores of employees, and we will have a series of on-site classes where the individual classes might be composed of heterogeneous groups of employees. Most of our trainings historically have taken place in the continental United States, so around North America, but many companies that are headquartered here will also have branch offices in other locations, maybe in India, maybe in Singapore, and we've trained teams there as well. Now, as far as our class offerings, they come in two major forms. So one of these are a comprehensive coverage from fundamental theories in Python to practical applications in some sort of given domain. So Python for Data Science is one of these comprehensive classes that takes students from data structures to building models within the span of 5 days. The second course offers intensive practice applying some library to real-world data. Pandas Mastery, for example, is one of these intensive classes that has students using all of the corners of the Pandas library to do things like clean and reshape their data. You can learn more about any of the classes you see on the slide by reading the descriptions on our course website or by watching one of the previous webinars online. Now, I'd like to take a little bit of time to talk about Enthought's training philosophy, which combined with our deep subject matter expertise is what sets Enthought apart as a training provider. All of our trainings are organized around one question, which is what will the students be doing when they get back to work on Monday? We build exercises where the students will practice doing those exact tasks with instructor guidance so that there will be a seamless transfer of knowledge from the classroom setting to the workplace. And I think most people find it intuitively obvious that it's not possible to learn how to ride a bicycle from listening to a lecture, and the same thing is true of programming. You can't learn how to program just by listening to someone talk about it. It's only after we've created the exercises that will enable that transfer of abilities that we create the supporting lecture. And the reason for this is that there is a general trade-off between the time spent cultivating some ability and the time spent listening to someone explain the concepts underlying it. A common feature of a poorly designed training course is that their topical scopes are far too broad, which results in a class where students feel like they've learned a lot, but when they sit down at their desks on Monday, they realize that they're missing the knowledge of how to use any of the things that they've heard about. At Enthought, we found that devoting roughly even amounts of time to lecturing and to exercise gives students enough practice to make them effective at work, while not leaving that practical knowledge unmoored from a conceptual understanding of how and why their software works, or more commonly, why it's not working the way they wanted. Now, Enthought is a scientific company, so we collect different kinds of metrics about the success of our pedagogical strategy and class structuring. And one of these is just verbatim feedback from the students, and I'll bring that up a couple of times during the course of the webinar. Now, the first ones that I'll show you address two deliberate choices we made when designing our training strategy. The first is the exercise-oriented structure of the course. Because our employees are subject matter experts, the exercises that they put together are realistic software use cases that are also illustrative of some core concept or strategy. And the second thing is that our trainings are all in person. This is a key benefit because the courses themselves usually end up getting tailored to the students' varied interests and backgrounds, and because the students will have a Python expert who is immediately available to answer any questions they might have. And now today, we'll be talking specifically about the Machine Learning Mastery Workshop, which belongs to that second category of intensive classes. The workshop is intended for people who want to use machine learning to solve specific problems in their industry. So for example, if you work for a company that sells consumer goods, you might want to construct machine learning models that forecast the demand for the products that you sell. You might want to build machine learning models that predict the failure rates of your machinery so that you can optimize the scheduling of preventative maintenance. You may also want to build machine learning models that look for patterns in product defects so that you can trace those problems back to some specific supplier or some contractor. Now, students won't need to know anything about machine learning before they enroll in this course. We'll cover all of the basics. However, because the course is only 3 days, and all 3 of those days are going to be spent on machine learning, the course will require that students already know how to use Python. Specifically, the libraries we introduce in the class depend heavily on NumPy and Pandas, so prior experience with things like arrays and data frames are going to be necessary to participate. And if you are unsure if you have the requisite background knowledge, you can enroll in any of the course offerings you see listed on the slide, as they provide a thorough introduction to these topics. The workshop itself is organized into 6 modules, where each module covers a single coherent topic. The workshop starts with a conceptual introduction to machine learning and an overview of its implementation in the scikit-learn library. Now, a common misconception about machine learning is that the difficult part is choosing some particular algorithm or some particular estimator, when in practice, your engineers and your analysts are going to spend the vast majority of their effort manipulating input data. For this reason, the bulk of the workshop is spent in the final 4 sections, which are focused around engineering features for specific kinds of input data. We start with the simplest case, which is numeric features, and progress through categorical, linguistic, and image features. In each of these sections, we'll present core concepts, best practices, common mistakes, and critical trade-offs. So we start here with our conceptual introduction to machine learning, because that knowledge is going to be foundational to the rest of the work that we do in the course. And here, we'll cover components that are common to all machine learning libraries. This includes different aspects of the data that we'll be concerned with, like its binary format, its legal values, its common values, whether it has special values. We'll also cover each of the components of an estimator, including its model or process, its loss or cost function, and its learning strategy or optimizer. We also cover the distinction between supervised and unsupervised algorithms, and the difference between numeric and categorical targets or labels. So this is an example of a title slide from the workshop, and this is a cue to you right now in this webinar that the slides you're about to see have been lifted directly from our training materials. In our conceptual introduction, we start off with a broad overview and some basic definitions. So machine learning is this idea that instead of telling a computer how the world works, we give it some set of beliefs and ask it to update those beliefs based on some data. So to take a silly example, I might want to have a computer program that tells me how tall I am based on the day of the week. The engineering solution to this problem is to write a program with some values hard-coded into it that say I am 2 meters tall because it is a Monday. The learning solution, on the other hand, is writing a program that believes my height changes each day of the week, and then uses actual observations of my height to figure out how tall I usually am on a Monday. That initial belief, that my height depends only on the day of the week, is what we call a model, and it is one component of a machine learning estimator. We drill down into this component using a common example to examine how a model uses data to generate predictions about the world, and what parts of the model are actually modifiable during the training of the estimator. Now, the purpose of going through these fundamental concepts is to create good intuitions about the behavior of machine learning programs. As we discussed earlier, a lecture is only one component of creating this intuition. What the students need is an object they can practice with. So after seeing at a high level where models fit in estimators, and then after drilling down into what models are and how they work, we give students the code for a dramatically simplified estimator. And the first method you see here in this estimator class is a real example of the model concept that we've been discussing. And in this particular exercise, among other things, the students will change that model and see how it changes the behavior of the entire estimator. Now, with an intuitive understanding of the basic concepts, we move into the API for scikit-learn. Scikit-learn is one of the most popular libraries for machine learning, but it's not because it is particularly fast or particularly efficient or feature-rich. It's very popular because its API is composable. And what we mean by composable is that objects in scikit-learn share a common interface, which makes it trivial to swap components into and out of machine learning programs. In scikit-learn, we have objects in the API that are estimators similar to the one that we've just seen. So they all have some internal state, which is modified with a fit method, and they all predict the labels for an observation with a predict method. And this kind of composability is crucial for rapid iteration. Now this is important because in learning software, when you're iterating over generating your product, that iterating step doesn't really end. So in practice, the use of learning software is sort of this continuous loop where we're constantly running our models, evaluating how well they work, changing them, running them, evaluating how well they work, changing them again, and so on. And scikit-learn is exposing objects here for combining these steps into a single estimator that we can loop over. And it makes it very easy to do this kind of a thing. So here again is the title slide for this portion of the class, and now in the same way that we drill down into each component of that estimator during the concepts module, we drill down into each one of these object categories in the API module. So we can take this pipeline object, for example, and see how to construct one, what its methods are, and how we can retrieve individual processing steps from it. Immediately after this discussion, where we have talked about how to create and use a pipeline, to facilitate the constant evaluation and modification loop, we have this simple exercise where the students practice doing that exact thing. So they're making a pipeline, they're modifying one of its attributes, and then they're using one of its methods. So we'll have something like this for each one of these objects, and then sometime later in the class, we'll end up on a synthetic exercise where students are given some task to complete that requires them to use all of these objects together. Now in this one particular exercise, students are combining different objects from the scikit-learn API to perform principal components analysis, in this case on human faces. So this is a great example of an exercise that is both a common machine learning task, so in this case we're using dimensionality reduction, and it also illustrates a very difficult concept. So PCA works by separating out orthogonal components in your data, which is a very difficult thing to conceptualize. So in this particular exercise, the students will see that there is some sort of average face, and each orthogonal component is a modification to that average face to produce a specific one. So the first principal component is usually whether the face is like lit from the left or the right. Somewhere down the line we see whether the person has a mustache or not. Now this three-part exposure to this particular concept is a core design implementation in our training offerings where the students are hearing about a thing, they're trying out that thing, and then they're using it to perform some real-world task. And we can go back to the feedback from our class participants, and we see that a major factor in the perceived quality difference between Enthought trainings and other trainings is exactly this instructional strategy. So our trainings include instructors who can help students understand a difficult topic in a way that is both individualized and immediate. And our training produces students who show up to work on Monday knowing how to do all of the things that other courses have only ever talked about. So now that we know how to leverage the power of these specific objects inside of the scikit-learn library, we can start thinking about the keystone of any machine learning effort, and this is the feature engineering step. And we'll walk through each one of these feature categories one by one. Feature engineering is this sort of umbrella term that includes everything from applying transformations to an existing feature to extracting wholly new features from some kind of unstructured or semi-structured data. Most of the performance improvements that are available to you inside of machine learning tasks comes from the practice of feature engineering. And since that's where you're going to spend your time in the real world, that's where we're going to spend most of our time in this class. Numeric features require the least amount of engineering effort, so that's where we'll begin. Now, when we say numeric, we don't just mean that the data is represented by numbers. Most data eventually is. What we mean is that these data conform to a specific set of expectations about their distributions. And in particular, to make these perform well in our model, we need to make sure that any relationships we're looking for are represented linearly inside of our data. And finally, we'll also walk through the most useful subset of machine learning algorithms for predicting numeric labels, and this is called regression. So again, here's our tighter slide showing some examples of numeric data. And in the class, we do this deep dive into every one of the topics you saw on the previous slide. For the purpose of this webinar, though, we're going to focus on that distribution factor. Now, as a motivating example, we can generate some fake arrays of data which are almost perfectly linear, and you see these here on the bottom plot. Above this is an exponential transformation of that same data. And now overlaid on each of these is a two-dimensional kernel density estimate, and what we see is that for the correct distribution, this works really well. For the log linear data, this performs very, very poorly. Now, one particularly convenient way for checking the distributions of your data is to compare it to a well-described continuous probability density function. So in Python, we have a set of tools in the SciPy library that fit these PDFs to observations, and we can pass these directly into the Seaborn library to generate visualizations that make it very easy for humans to compare. In addition to nonlinear transformations, many of the machine learning algorithms in scikit-learn expect to see data that are normalized. Different objects that will do this are located inside of the pre-processing sublibrary of scikit-learn. We don't do an exhaustive walk through every single option that you have. Instead, what we've done is we've selected out the 3 most useful linear transformations, and we've given you simple if-then rules about when to use each one. Immediately after talking about the methods in scikit-learn for scaling data, we give the students an opportunity to practice using one of them on a small built-in data set. And again, there isn't anything complex going on here. I'm just using a single object to see how it behaves. Sometime later, after the students have had the opportunity to see regression, to see bivariate visualizations, they're given the synthetic exercise where they need to combine all of that knowledge about transforming and visualizing and predicting. And in this particular case, the task here is they're predicting wine qualities. In this particular slide, what we're seeing is sort of the punchline of this exercise, which is that the quality rankings are very nonlinearly distributed. And specifically, you'll see that almost everyone rates wine as average. Now, if you haven't performed some kind of transformation on the target values, if you haven't corrected that nonlinearity, any regression model that you train will essentially continuously predict that average case. So here on the x-axis, we have the actual real-world ratings. The y-axis is the predicted ones. And what you'll see is that the predictions, with I think one exception, are all either 6 or 7. So just like before, they've had this chance to hear about linear and nonlinear distributions, to practice linearizing a distribution in a very simple case, and to apply that knowledge in a real-world exercise. Now, what makes our workshop intensive style classes different is after our layer of synthetic exercises, we have another layer of exercises that we call case studies. Case studies are contemporary computing tasks that are designed to give students structured experience using real data to answer real questions. So for example, you might be someone who works in agriculture, maybe for a company like Conagra or John Deere, and what you would like to do is predict the grain supply available in each country. So you collect some numeric data about temperatures, maybe about rainfall, and none of this data is clean, so we have some missing observations, we have some invalid data. In the case here, the case study is to predict how much grain is produced in a country in a year. And now one particularly clever thing you might try to do is say, I will try to predict the grain output based on the area, the square kilometers of farmland. Now, the initial attempt we see here on the left-hand side, it produces a very, very poor model, and we can understand why if we look at that graph. So we're seeing the same sort of linear dependency in the sparsity of the data that's characteristic of log linear data. Now, if we log transform these data, we see the results here on the right-hand side, and this is a very, very strong factor, a very strong predictor. And this ends up producing a more accurate model using this feature, which initially appeared to be unrelated and unimportant. Now, if you've been counting, this is 4 separate exposures to this idea of linear and nonlinear relationships. The concept, one method for transforming data, handling nonlinearity in a controlled exercise, and then handling nonlinearity in uncontrolled real-world data. The other major topics for numeric features, things like support vector aggressors, things like trellis plots, all go through the same system of repeated exposures that move from the simplest task all the way up through exactly the kind of work that students will be doing when they return on Monday. So now that we have this solid grounding in numeric data, we can start talking about other kinds of features. And the next one we'll talk about is categorical features. Now, while categories are usually represented by numbers, we said that they are not numeric because there are no guarantees that the distance between category A and B is the same thing as the distance between category B and C. Now, because of this, categories have their own special concerns for plotting, for feature extracting. If they're labels, there are some special concerns for modeling. And again, we're going to cover each one of these topics in some detail during the workshop, but for this webinar, we're just going to sort of highlight one of them. And our highlight is going to be the strategies that we use to evaluate the success of predicting categorical labels. So again, we see here our title slide of some examples of what might be categorical data. And now the reason that we have special concerns when our predictors, our predictions, are categories like this, is that when we had numeric data, our concept of error was some very simple distance metric. What was the prediction, what actually happened in the world. Now with categorical labels, we don't have that same concept of distance, so what we do is we label each individual prediction as correct or incorrect, and then we use some strategy to combine all of those into one single number. Now the choice of this strategy is very important for classification tasks, and this is for 2 reasons. The first, because sometimes we care more about one kind of error than another. And the second, because these metrics are sensitive to the distribution of targets. So if you choose the wrong one, you can get a very misleading estimate of how well your model is performing. So once again, after describing the concept of evaluating classification models, we immediately move into a simple exercise with the intention of using several kinds of metric on a simple result to see how their output differs. In this particular case, the data we are predicting is manageable enough that if the students want to, they can compute these same metrics by hand to see where those numbers are coming from. Some time later, after we've covered the other topics, like predicting categories and classification, we move into a synthetic exercise that involves assigning numerals to handwritten numbers. So this is a pretty well-described task, given that your input data fits some conditions, so here everything is already centered and it's normalized. And on a task like this, it's pretty trivial to achieve accuracy that's higher than 90%. So if we want to tweak the performance of our model, a single number summary probably isn't enough. What we want to do is use a diagnostic tool called a confusion matrix to visualize which inputs are incorrectly labeled and what those incorrect labels tend to be. So you can see all the zeros here in this matrix. We're not making a lot of errors, but our worst performance seems to be centered around predicting from the number 8. So maybe our images have the contrast pushed a little too hard, and our model would perform better if that was dialed back. After a number of simple and synthetic exercises, we move into our case study for categorical data. So again, we are using real-world data, but in this case, we are using sets of categories for individual countries about things like their propensity for natural disasters, things like their system of government. And the task here is to detect countries that have a high risk of famine. And again, these data haven't been cleaned, so we see that there's some missing data that will need to be handled. Some of these labels here are combined into one column, and those will need to be split out in the table and so on. So a first attempt to building a model for this task will work almost perfectly. Here we see something like a 98% accuracy. Now the reason for this is not that the model is actually working. The reason is that the default evaluation in scikit-learn is the unweighted accuracy, which is just the total number of correct predictions divided by the total number of predictions. In this particular sample, famines occur in less than 2% of the cases, so you could achieve the same accuracy by just ignoring the data entirely and predicting that no country will ever have a famine ever again. So we can substitute a different evaluation metric that we talk about during the workshop to get a more representative value of the value added in this model. which in the current case, since it's not predicting anything, is a value of 0. It has no value for us. Now, during the class, of course, we would go through the steps you can take to make this model perform better. 0% is very, very poor. But for us, what we would like to do is move on to the next major kind of feature. And these are linguistic features. Sometimes you'll hear these called natural language features as well. So generally speaking, what we're going to do is go through a process where we are converting human language, typically represented as strings of text, into some kind of numeric or categorical label. Now, we might think of this as measurement, where we're measuring some aspect of the language signal in the same way that you might measure aspects of things like the weather. The key difference here is that we're doing our measurement in software and we're not using something like a thermometer. Now, natural language is somewhat unique in the world of signaling in that it carries multiple simultaneous channels of information. These might be as simple as the mood of the person who is talking. These might be as complex as some dialectically negotiated socio-political role. Now, a few of these channels have common software implementations because they've been shown in practice to be very, very useful in machine learning models like the ones we talk about in this class. So we'll be talking about one of those channels, the lexical channel, during this webinar, but of course the class will go through a handful of the other ones. We'll spend some time working through things like the long tail problem, or when you should use the lemmatizer instead of a stemmer. So here again is that title slide, so we're moving into actual content from the class. Lexical and that lexical channel is a term that just means it's words. So the lexical channel is concerned with how often specific words appear. So for example, if I'm trying to classify articles by whether or not they're about food, there are individual words that are going to be very good indicators of this, like the word pork or the phrase ham meat. Now, for our purposes, for this classification purpose, the distinction between pork, comma, with ham, and ham, comma, with pork is not really useful. So, generally speaking, we disregard the syntactic information. We can drill down into this concept of features, and we see that we are creating equal length vectors for each one of these observations, where each feature in the vector is stably but arbitrarily placed. Now, the distinction we're making on the slide here is important because we live in the scientific Python world, and in scientific computing, we typically use the word vectorize to mean mapping a function across some data structure, maybe an array. However, in this specific context with linguistic data, the word vectorizing refers to the process of converting a string into a vector that has numbers inside of it. So now that we have introduced this information channel and the concept of vectorizing, we can go through a quick example where we are creating an instance of that vectorizer and we are making a couple of changes to it. So for example, we are seeing how stop words interact with that vectorizer and what happens when we modify that n-gram range. Now, this particular question is also giving the students exposure to some of the problems that we saw in the intro slide. So in particular, they're going to run into that long tail problem here. Sometime later, after we've covered the other topics, we'll move into a synthetic exercise that asks students to classify movie reviews into positive reviews and negative reviews. And this is a pretty classic natural language task. Now, the data here are all pre-cleaned, they're pre-processed. You can notice there's spaces between the words and the punctuation. That's a pretty good indicator of that. In this particular exercise, you have sort of one tool to play with, which is how you can vectorize this particular amount of text to generate a model that performs the best. So you might try something like a semantic vector. You might extract some orthographic features like the length and characters of the review. But in this particular genre of writing, simple count vectors tend to work pretty well. So we can run one of these and look at the importance assigned to each particular word in our vocabulary. So we see a lot of things that you would expect. So if someone uses the word boring, it's probably a bad movie. But there are some things in here that you might not have expected. So for example, if people are talking about the writing, like the screenplay, that's a strong indicator of a movie that was very, very bad, that people did not like. On the other hand, if people are talking about the performances of the actors and the actresses, this is a very good movie. So if I'm someone who works at a movie studio, this might be something I would want to know. It's not something I might have expected, it's not something I might have looked for, but this is a pattern that's been uncovered by the algorithm. So we finish off our linguistic feature section with another case study. In this case, we are again trying to predict famine risk for individual countries and individual years, but in this case, we are given expert analyst reports about things like the country's economy, about their political history, about environmental issues they're currently facing. Now, this particular case study isn't going to be solved simply by constructing a lexical vector and feeding it to a learning algorithm. And the reason is revealed in the shape of the resulting training set. We see that we end up with 56,000 features, but only 4,000 observations. So this is a really good exercise for giving students practice in dealing with poorly shaped data. The final kind of feature that we'll cover here in the Machine Learning Mastery Workshop is image features. So images are different in that they're typically numeric in their storage format already, but we almost never want to predict based on the individual values of specific pixels. So instead, we're going to go through a similar set of steps where we are extracting useful features, useful vectors from that image to make a prediction. So we're going to be measuring things. So we're still going to be concerned with things like normalizing our data. We're going to cover things like transforming the images, restoring the images, filtering data out of the images, and the other topics you see listed on this slide. For this webinar, we're just going to go through one, and that particular topic is segmentation. So here's our title slide. We're about to start talking about the materials in this class. Segmentation is this action of splitting an image into separate areas, usually because you care about one area and not another. So for example, I might want to do something like segment out this coffee cup from its background. Now to a human, this is pretty simple. We understand, for example, that white rim is part of the mug, but to a computer, this is a very difficult problem. And if you ask a computer to segment this image, typically it'll find the espresso, it'll find the white inside of that cup, and then it will find the red outside of the cup. It's three separate things. So as part of our segmentation discussion, we talk through the pros and cons of different strategies for segmenting images. One of these relies on finding the the edges between objects. And what you see here is the Sobel algorithm. This is a computationally efficient way to do this, but it tends to perform poorly on images that have lots of detail. So just like before, immediately after we talk about it, we have a chance to practice it on a very simple case. So this is a built-in image of just coins on a black background. And then some time after that, we have a synthetic exercise where the students practice different segmentation methods on different kinds of images. So the one you see here, this is a very artificial image, and it's giving students an intuition about how that watershed algorithm works by giving it data that has no kind of elevation information. So we finished our image processing section with our final case study. Again, we're trying to predict the amount of grains produced in a given country in a given year. But unlike that first case study, what we now have are satellite image tiles that are taken regularly across the entire planet. We can see in this particular example here that part of the image is missing. There's clouds covering part of it. There's a very strong difference in luminance where those two images were stitched together by the satellite. And these are all things that are going to cause problems for any kind of image processing that we try to perform. So in this case study, the students will need to devise strategies for extracting different kinds of information that will be useful in predicting agricultural output. So for example, the students might segment out just the land, so ignoring the lakes and the oceans, to estimate how much dirt belongs to a particular country. In this kind of real-world experience is what will make the difference Monday morning when the students in this class go back to their work. We can teach it because we know it. Our instructors all have advanced degrees in relevant fields, coupled with real experience writing software in Python. And they're all very passionate about what they do, and this matters, like the students notice. And this is probably the most common feedback that we get, that our instructors are among the best these students have ever encountered. And because of this, because of our instructional design, because of how amazing our instructional materials are, more than 95% of attendees would recommend a class that they took from us to a colleague. So speaking of instructional materials, we release some of them online for free from time to time. Earlier this year, we released a set of desk references for the more common machine learning estimators inside of scikit-learn, and you can download these for free by going to enthought.com/python4 science training. Now, we mentioned briefly at the beginning of the webinar that we serve trainings to clients across several different industries. To be more explicit about the global applicability of our trainings, we have a slide here with the logos from a subset of our clients, the more publicly recognizable ones. You'll see that the broad categories include oil and gas, military applications, aerospace, consumer products, electronics, biotech, banking, finance, and agriculture. So if you're an individual and you would like to take this class, maybe you work in one of these industries, maybe you work at one of those specific companies, you should visit enthought.com/training, where you'll see a calendar of our open classes. So these are classes where you can choose a date and a location that works for you and register for the class as a single individual. If you have a small team that you manage and you're interested in having a class locally to where you are, please get in touch and we can talk about setting up an open class for your location. If you have a larger team, or maybe you're someone who manages the trainings across your entire company, you can please contact us by email at info.enthought.com or by phone at 512-536-1057, and that will put you in touch with one of our account executives, either Brian Allison or Michael Millette, who you see here on the slide, and they're available to help you find the best Python training course for your own needs, whether that is this machine learning workshop or whether that's Python for data science. Now, after the webinar, I have a couple of questions I'd like to ask you. I'd like to know whether it was useful, if there were topics you wanted to hear about that we didn't cover. So you'll see a survey pop up when it ends. We really do appreciate your feedback, so please fill it out, and we do incorporate it in future webinars. But right now, I see that you have some questions for me too. So I think this would be a good time to move into the Q&A.
Well, Dylan, we've really had some great questions from the audience here, and from what we can tell, people really enjoyed the material. So thank you very much for introducing everybody to the Machine Learning Mastery Workshop.
Of course.
So at this time, if you do have additional questions, please feel free to put them in this questions panel here, and I'll throw them over the fence here to Dylan. But in the meantime, as promised, I'm going to pull a couple that have already been asked. So, Dylan, you did just now mention the Python for Data Science course. Could you answer two things that people have asked in here? One of which is, what's the difference between the Python for Data Science course and the Machine Learning Mastery Workshop? And then secondly, do people have to have taken an Enthought training course to attend the workshop, or are there other ways that they can be prepared for this?
Thank you. That's a terrific question. So we do offer two classes that are Data Science E. One's called Python for Data Science, and one is this Machine Learning Mastery Workshop. So the difference is the Data Science class is a 5-day class that takes you all the way from sort of fundamental beginnings up to building models. So it is very, very fast paced. You're covering a lot of ground. This Machine Learning Workshop is a 3-day long class where we're not going to cover that broad of a set of topics. We're going to focus very specifically on the machine learning portion. So we will expect that you already know Python, you already know NumPy, you already know Pandas before you show up. And you don't need to know any of those things for the data science class. Now, if you would like to take the machine learning workshop and you don't know Python, I would highly recommend taking our Python for data analysis class. That will get you everything you need to know. But maybe you have used NumPy somewhere else, you've used Pandas somewhere else. I mean, if you feel comfortable working with arrays, then you should be okay in this class.
So as a follow-up to that, Peter actually asked what you would suggest for somebody coming from SAS. He says, what would be your suggestion, given that I know SAS 10 plus years and have a technical college background from MIT? So what would we tell Peter here?
That's a great question. Thank you. So of course, what I would like to recommend to you is Python. If you have been using SAS, moving into R will be sort of less of a transition energy for you. Since you did come from MIT, maybe you want to pick up Scheme just to show your school spirit. But Python is one of the tools that it's I think the most widely used language right now for machine learning. So if you're trying to get into these kinds of modern analytic tasks, I really do think that Python is the way to go, and that's why we teach the class in Python.
And as a follow-up to that, and what we were just talking about with Python for data science, Richard asked if you could elaborate on how much Python you need to know for Python for data science.
That's a good question. So you don't need to already know Python to take the Python for data science class. Now, we do strongly recommend you've done some kind of programming before. So if you don't know what a loop is, for example, the Python for data science class is going to be too fast-paced for you. But if you're familiar with the idea of a loop, a variable, like if-then statements, you can feel free to sign up, and I think you'll do well.
Okay, got a hard one for you. So I'm going to limit you to 30 seconds on this. 30 seconds for the age-old question. Which one is better for data science, Python or R? Now, you have strong feelings on this, so in 30 seconds.
In 30 seconds, I would say use the right tool for the right job. R has some very good tools for data analytics. So for example, I still use R, and I use R all the time. But what's nice about Python, and what makes it a better language for this in my opinion, is that it is much easier to integrate Python with other systems on your computer. So no one ever does data science in isolation. You need to talk to all kinds of databases. Maybe you're retrieving data from Kafka, for example. That's going to be easier to do in Python than it is in R.
Okay, great. And concise and good reason to possibly know both languages, but why one versus the other? All right, so probably one of our most popular questions today, and we saw this one coming, by the way, was will deep learning concepts and related Python-based approaches be covered? So let's talk a little bit about deep learning here, Dylan.
So the answer is no, not for this particular class. And it's not that we have anything against deep learning. It's fascinating, and we're all really excited about it here at Enthought. But for us right now, what we wanted to focus on was a machine learning model that could be applied to all different kinds of things and was usable on commodity hardware. So typically we have people in our classes where the only processing power they have is their own laptop. Maybe they have a dedicated server somewhere, but these are typically not GPU-enabled servers. So we wanted to first offer the class that is the most widely applicable, the most widely available, the lowest barrier to entry, and sort of pay attention to what we'll offer at a future date. This might be in the pipeline.
May or may not. We won't disclose. Okay, we've got time for probably two more questions here. So this one's a good question that we also hear a lot. It's a little bit more general to machine learning, but they'd like to know, can someone use machine learning for image analysis? And the example given is, for example, detecting cell boundary and tracking multiple particles. So machine learning for image analysis.
So the particle tracking is not something I personally have experience with, but detecting cell boundaries, absolutely. So the same thing that we had just been talking about, so things like finding edges, things like segmentation. We didn't cover this in the webinar, but in the class we talk about separating color channels, for example. So if you have histochemically dyed cells, you can separate things out that way. Absolutely, you can do that here.
Great. And one more. Okay, I'm going to cheat and do two more because we just had one more good one come in. So we were, will this class teach naive Bayes systems? Bayes.
Yeah. Actually, no. No, it doesn't. So if you sort of take an introduction to machine learning class online, they usually walk through the naive Bayes classifier, specifically for linguistic tasks. In our experience, it tends to perform pretty poorly. There are better models to use, so instead of teaching about a model that's not useful, we spend that time focusing on things that work better. In this case, we would probably use something like a support vector classifier.
Okay, that's good information for people to know. So final question here. What do you use Python for knowledge-based recommender systems? Is that a good application for machine learning and machine learning in Python specifically?
Absolutely. So this isn't something that I do as a person, but yeah, if you're doing something like collaborative filtering to recommend things like books or music selection, Python is a great library to get started in for that.
Okay. Well, I think we've covered some great use cases for machine learning. Thank you again, Dylan, for doing this and for doing it live. And thank you for everybody for attending today. If you would take just a minute and, as Dylan mentioned, give us a little feedback on a very short survey, that really is helpful to us in future development. And you'll see that come up on your screen here momentarily as we end the webinar. Again, thank you for your time today, and we hope to see you in a class soon.